Hello guys, welcome back to the LearnRISC-V channel. So this session discusses the most common bit operations like a bit set, clear and toggle, which are very much needed in system programming. So starting with how to use Boolean operations to set, clear and toggle bits with bit mask followed by the implementation. So this implementation would be specific to RISC-V instruction set architecture and uses the RV32I logical instructions, which is already discussed on the suggested video above. So if you haven't watched that, I would highly recommend you to watch that before continuing with this. And in the second half, I will discuss about how to write a generic and reusable GPIO HAL or hardware abstraction layer using this bit set, clear and toggle operation. And I would use it to blink the blue LED on the hifive1-revb board. So before we get into the bit operations, or before we get into the implementation or concept of this bit operations, so one application where this bit operations are most commonly used is while configuring the peripherals. Let's see an example in FE310 here. So each block here corresponds to one GPIO pin in FE310. So totally there are 32 GPIO pins, and the pins are numbered from 0 to 31, same as the bit positions on a 32-bit register. And each pin, if you see here, can be configured as an input pin by enabling the input enable, or it can be configured as an output pin by enabling the output enable. And the pin can be raised high or low on the output side by writing values into this line, or you can read the value from this pin if it is configured as input. So this pin configuration, or the GPIO pins, are configured using a set of memory mapped registers. That means that a set of registers which are memory mapped, you write those values corresponding to configuring them as whatever the way you want that to be, and then you can write those values. So if you take the blue LED blink code in the Git repository of LearnRISC-V, where the GPIO pin number 21 is connected to an LED on the board. So the code would just write 1 into this memory mapped address at bit position 21. That would blink the LED, and to turn off the LED it would just write 0 here. Okay, so this is just one example how this bit operations are used. So this slide has the Boolean logic operations OR, and exclusive OR truth table here, and you can find this on any of the digital electronics book. The reason it's here is that these bit operations of set, clear and toggle are achieved using these basic Boolean logic operations. So let's see how a bit is set using this Boolean logic OR operation. So here you can see the truth table, and the first row corresponds to the present value in the memory map register, and the second row corresponds to a generated mask, and the third row is a result after performing the OR operation or bitwise OR operation. And this slide discusses the bit set on 21st and 7th bit position. So the 7th and 21st are highlighted in red. So the fundamental things that to be considered while performing this bit set is that the state of the other bits should not be changed. So except the bit on which this operation is performed, all other bit values should be the same before and after. That's one of the recommend. And result should not vary. Result and operation should not vary based on the present state. That's why the other example, so one example you can see here, the initial bit position is 0, and the second example is with the initial bit position 1, and these are the two states of the Boolean logic. So this generated mask has a value 1 on those bit positions alone. So for the, let's see the first example of 21st bit position. So initial value is 0, and we generated the mask with the bit set at the 21st bit position, and then bitwise OR is performed all through this 32 bits, and this is the result. And you can see that the bit has been set and other bit positions are not changed. And the second example, which is the 7th bit position, the initial value is 1, and the bit mask as a 1 on the 7th bit position, and if you OR, and the result is the bit is set and other bit positions are all retained as such. So in the truth table, the highlighted rows in green, so the properties like 0 or 1, the initial states. When you OR with 1, you can say the bit is set. So these two rows are the properties of the truth table, is the one that is used to set the bit. Now to clear, so this slide discusses the 21st and 13th bit clearing, and it would also cover the initial states with 0 and 1, because those are the two states. And so this is the initial value in the register, and here we generate mask like before with that bit position alone set as 1. Then we invert the mask so that a 21st position alone is set to 0 and rest are all as 1. Then you perform an logical or Boolean AND operation on each bit, and this corresponds to the result. And again, as you see, the other bits or other bit values are retained as such, and that's the basic requirement. And also the initial state for 1, and if you see another example with 0, it should clear the bit irrespective of this initial values. So in the Boolean logic AND operation, so the first row and the third row, the properties of these two are the one that's used. So the operand or the initial values can be 0 or 1. When you AND with 0, it becomes 0. Okay. And as you see, without this inverted mask, if you just clear, then you will not be able to achieve, or you will not be able to satisfy all these requirements. Okay. So now let's see the bit toggle operation. And so bit toggle is nothing but, okay, so this is I should have removed this, but it's okay. So this is the initial value of the register, and we have the same mask for 21st bit. The mask is 1 here, and this bit toggle is achieved using exclusive OR. So 0 exclusive OR of 1, so this becomes 1. That means that the bit is toggled from 0 to 1, and on the same bit, if you apply exclusive OR again, then it becomes 0. So these two rows, so 0 and 1 becomes 1, and if the initial state is 1, then the result it's toggled to 0. Okay, so this is how the bit toggle is achieved using exclusive OR, and as I say that this depends on the present state, because toggling is like if the present state is 1, then after toggle it should become 0 and vice versa. So now let's see the GPIO code, which is already there in the LearnRISC-V Git repository, and the release branch has the blue LED blink code. And if you see, this is the current HAL, or I would say the current at present, this is a function which is used to write 1 or 0 into the GPIO memory map registers. So when I started very first, I just want to get quickly with the board and see this LED blinking. So I just wrote a code like this. All you have to do is like pass the value in the A0 register. Okay, on the right side, this would be easy. So this is the code as such. So this is a function, and to blink GPIO 21, I set this a value with the bit position 21 set and pass that to this function, and this function would just write this value into this memory mapped register, which would put that into the GPIO pin. So this is how the LED was lit, and then I just write A0 with the A0 register with the value 0, and that would put off the LED. But if you see here, the problem with this that this is, let's say that if I want to lit another LED, then so it's very, and if I just lit that LED on a different bit position, then this LED on 21 would be turned off. So this works well for a hard-coded 1-bit value, but this is not generic reusable. But this was okay just for one application to start bring up the code to see to speed up the initial ramping up stage. So what I'm going to do now is to change this HAL layer to have these two functions. This is how the normal GPIO HAL would look like. So GPIO set high, and you just pass the pin number, and that should be set high. For example, for GPIO 21, you just pass 21 to this, and whatever is connected at the GPIO 21, that has to be, the pin has to be set high, and to set that low, that pin has to be set low. So now these two functions, when pin number is passed, the other bit positions should be retained as such. So that's how it should be implemented, whereas in this case it's not. For example, the passed in value is like it's a complete 32-bit value, whereas here you can just set high 1 by 1 GPIOs, or you can set one GPIO high and other GPIO low. But the code should code the code RISC-V code should go here. So soon we will write this code and test that. Okay. So let's start with the coding now. So GPIO.s in the hifive1-revb board directory is the file which has all the functions related to GPIO. So this is the one which we need to modify. But what I can do is, instead of modifying that, let me first create this as two new functions. So register A0 has the GPIO pin number, and so basically it involved three steps. One is get the GPIO number, then generate the mask, then perform Boolean or bitwise OR operation. So that would set the corresponding bit high, whereas to set low, see, generate the mask, then invert the mask, so the set low had 4 steps because the additional step is to invert the mask. Okay, so to generate the mask, let's write a simple function which would, so this function should get the pin number and generate a mask, right? So GPIO underscore generate mask. Zero has the GPIO number. So now if the GPIO, so this can be between 0 to 31. So GPIO pin, so if the input is 1, okay, it can be between 0 to 31. So if it is 0, then we should return 1. So branch equal to 0, 0. You branch to GPIO 0. So this is a special case where you return, so load immediate is 0 with 1. If not equal to 0, then ly shift left logical destination is T0. So this is like shift left 1, shift left by GPIO number. So will this work? So if this is 0, then the bit position 0 is set 1 and A0 is returned. If it is 1, so this would correspond to 234, 234, 234. 4, 8, 12, 16, 20, 24, 28. Perfect. And this should be like, so if it is 0, this bit is set. Perfect. And if it is, let's say if it is 3, then this would be shifted to 3 1. So yeah, 0 1 2 3. Perfect. So this should work. And shift left logical, and let's keep the result in A0. If it is 0, then it would jump here, and that's fine. Now once this mask is generated, the mask is in A0, so what we are gonna do is perform the so the mask is generated, and first we should read the value from the register. So how do we read? What is the base? Okay. Line, and what is the macro for out value? So that is an include, GPIO include out value offset. Okay. Load word A0. So in RISC-V, as you know that you can read with in one instruction you can read from a memory offsetted by a value up to 12 of certain bits. So this would be very handy whenever you read from an offset. So we have the base address in T0, and with an offset of this from the memory, that value would be read into A0. Perfect. Now then we do the bitwise R, but if we read into A0 will be overwritten. So what we do is, let's read into T0. We don't need T0 values anymore, so let's read this into T0, then R. T0, come on, A0. Then store back. No, let's read into T1. T1, then store back A0 into this. See. Okay, so read the value into T1 and perform the bitwise R. So the A0 has the mask, and T1 has the registered value. We perform the bitwise R and store back into A0, and then this A0 is written into the memory location at this offset, which is nothing but the A offset to write the output value. Okay, perfect. So let's see if there is any. Shouldn't be. Okay, there's no compilation error. Good. And same, call the Let's see, generate the mask. So not of A0 comma A0, that would invert the mask, and then it's almost the same except that bitwise, and write that, and we have the A0 here and operation of A0, and this should be good. Awesome. So next I should just use this to set high and low in the application code. Let's hifive GPIO 21 as 21. And in the last loop, instead of writing the value like this, let's v and call this function first to set what was that? Yeah, this is set. So set high and let's see, here it should be set low. See, previously I was just writing all the bits with 0 just to turn off one GPIO. So A0 21 GPIO set low. Perfect. This is if test. Okay. Okay, there is a, so this is the main one with the delay. Okay, here there is no delay. Okay, so I think this piece of code I just wrote to test. So the main, this code should be more C set 1 and let's see, set 0. So now it's changed here as well. Then there's a delay and all good. Undefined reference. Okay, that's because global and okay. So let me connect the board now and see. What is the address? So this function is not getting called at all. So what should be wrong here is okay. Let's do one thing. So at times like this, it will be easy to debug with GDB. So what I'm gonna do is we set this flag and build again. So why this would be easy to debug as if you debug with this code, then there's a delay. So stepping inside these many times would be hard. That's why I had this block. So let's see if we can keep a breakpoint. So set high control GPIO is at okay, so now we have hit this point. Now see, so this would display the instruction next to the program counter. So next, as you see, it's loading this value 21, and set high. Why it keeps return as okay. So that's the problem with not saving the return address. So all you need to do is w RA0 of SB. Okay, before you call the mask, and right after that w RA, same should go to the high as well. So this when a function is called from another function, it's important you save the return address into the stack, and when you get back you read from that. Otherwise the register, the return address in the REA register would be overwritten. That's why you see here. So from the set high, the return address would have been set back to the this line, but now since I didn't say, what would have happened is when this function is called, the REA would have been overwritten with this with this address. So that's why you see that set high has been called again and again. Okay, now this should be fine. Let's see. So as you know that it's important, but as you see that I didn't add backup all the registers which are used, because I know that what all the registers are used in each function. But as we go on, each function will be improvised. So let's try again. Set a breakpoint and control GPIO loop, and let's run up to that first, and then let's display the instruction at the program counter. So right now it's at this one, and step I, this should call the set high, and okay, so now did it go into the, oops, okay, another problem here is that if you see in the generate mask, so once we have this, then we should return from here. So on this condition, it should show and return 1. Okay. Otherwise, this would execute this, and then again A0 would be set with the value 1. So let's build again. Now let's see the new address of this control block. What is the new address of the so oops, okay. Let's run up to that, and so right now we are this code. PC and Pi. Let's see first if this high is set, generate mask, return. Alright, SW, return, good. Now up and set low. Once this set low is done, the generate mask, set low, AW, read the value, perform the AND. Once it's stored, then the LED should blink. Oh yeah, there we go. You can see on the camera on the top, you can see that the LED is glowing. Now all you need to do is just stepping up. Once this comes to the high, it will be switched off because this LED is pulled up. So setting 1 would make it 0, and setting 0 would make it lit. Okay, so that's pretty much, and I hope you enjoyed this session, and please let me know about your comments on this implementation of this GPIO HAL functions, and if you also know any other way of optimizing these 3 functions, like on the bit clear, instead of generating a mask and inverting it and then is there any other way? But it should be reusable and it should be generic. Okay, so let me know if you have any comments on this. You can also see here the wire connections between the board to the OLED display. That's the work in progress, and this GPIO HAL layer has to be changed or fixed because this SPI interface overlaps with the GPIO HAL because each pin is multiplexed for different functionality like SPI or GPIO. So that's why I have to fix the GPIO HAL before continuing with the OLED device, OLED driver. Okay, I'm able to, so the progress on the OLED driver right now is I'm able to just blink on and off. So once I have the next set of functionality just to write some data, then I would publish very soon another video on that. Yeah, thank you and see you in the next session.